Good morning, everyone. I'm Erika Lia, and today we will focus on a specific sport application. In fact, we will discuss about jump performance evaluation, from acquisition to data interpretation. If you have any questions, it will be a pleasure for me to reply to you at the end of this webinar. So, let's start. Before starting the practical session, I will give you a general overview of how jump evaluation has been used in the past. There are two principal branches, which are force plates and optical cells contact mats. In both cases, height computation was derived by applying the equation of free fall to the motion of the center of mass during the flight phase. From this moment, the center of mass we will call COM. This phase is defined as the time between takeoff and landing. As regards force plates, they have been widely used because of their high accuracy, but they are expensive and they cannot be easily moved. For this reason, optical cells contact mats, which are portable, have been and they are currently highly employed. The unique weakness is that the field on which they will be positioned must be flat. More recently, the introduction of optoelectronic systems made biomechanical motion analysis more complete. In fact, by positioning reflective markers in specific anatomic points, it is possible not only to evaluate kinetics and jump height, but also kinematics parameters such as joint angles or, for example, trunk bending. As though for force platforms, the price of this advanced technology makes difficult its massive use, although its great advantages, such as its use in opening and lightening spaces. The difference between force platforms contact cells is that while the former calculate jump height through flight time method or impulse theorem, the latest use directly markers relative position. There are many publications in which advantages and disadvantages of technologies are described. In particular, Linton et al. Demonstrated that flight time method and impulse theorem method differentiate each other of about 0.5 to centimeters. Flight time method seems to overestimate jump height. Moreover, there is a condition that makes each method weak. In fact, impulse method accuracy depends on the correct determination of a specific moment before the jump where the subject is stable, while flight time method's accuracy leans on a perfect match of COM's height at takeoff and landing. With the arrival of three-dimensional accelerometers, most of the previous limitations have been overcome. Let's have a fast glance at the hardware. BTS G-sensor is a completely wireless inertial sensor. It consists in a three-axial accelerometer measuring acceleration in the three axes of the reference sensor system, a three-axial gyroscope measuring angular velocities, and a magnetometer. The communication method by which the sensor interfaces itself with the computer is a Bluetooth connection. This has a range up to a distance of 20 meters, but can be enhanced using a more powerful Bluetooth receiver. This particular device has two different employment modalities. The first one is the so-called online mode, in which there is a continuous data flow between the sensor and the computer. This makes possible to see raw data in real time on your personal computer. The second one is the batch modality, which allows to collect data on board and download them in a second time. Inertial sensor advantages are that it is portable. You can use it in all field conditions, no needing of a flat surface, Head computation doesn't have to pass through flight time or impulse methods, and they are cheap in respect to other technologies. Moreover, it can consider and afterwards correct trunk bending thanks to gyroscope correction. For further information, please see Piserno's work listed here. For a jump evaluation, BTS G sensor has to be positioned on L5 so that we can assume that it almost coincides with the center of mass. There is a dedicated belt in which the sensor has to be positioned, as you can see in this figure. BTS G Studio is the software that we give up with the G sensor. It is a very user-friendly and intuitive interface. No particular ability or previous prerequisites are needed for its correct use. So let's start with the practical session. I run the G Studio software. This is the main screen. We proceed firstly creating a new patient. So we click on Patient, insert New Patient, and we fill out all the data fields which are essential. So, for example, BTS test, 60 kilograms, and this is the height. We select the gender, and we click on Save. We confirm. Okay, and this is our new patient. Once we have done this, we click on Jumps Protocol. As you can see, we have the chance to perform 7 different kinds of jumps. Let's see in detail each type of jump. The counter-movement jump test aims at evaluating the explosive force due to elastic energy stored during the stretching shortening cycle. The subject starts in an upright position with feet at shoulders distance and hands on hips. Then the subject jumps after doing a counter movement downwards up to a knee bending of 90 degrees. During the test execution, the trunk must remain in an upright position. The squat jump test, here, aims at evaluating lower limb athletes' explosive force, starting from a knee angle of 19 degrees. The athlete, starting from an upright position and hands on hips, performs a squat up to 19 degrees knee angle and maintains this position for 1 second. From this static squat position, performs a vertical jump without make any counter movement downwards to keep out elastic energy contribution. If the subject makes a counter movement, the test has to be repeated. The counter movement jump with arm test aims at evaluating the explosive force due to both the elastic energy stored during the stretching shortening cycle and the upper limb coordination. The subject starts in an upright position with feet at shoulders distance and hands on hips. Then the subject jumps, helping himself with both arms, after doing a counter movement downwards up to a knee bending of 90 degrees. The repeated counter movement jump gives information about viscoelastic qualities of lower limb muscles, and it is used to evaluate metabolic process characteristics that support muscle work. The subject performs a series of vertical jumps all times after doing a counter movement downwards up to a knee bending of 90 degrees. The test duration can range between 15 and 60 seconds, depending on the athlete's qualities to be investigated. During the test execution, the trunk has to remain in an upright position. The squat jump body weight test allows the measure of lower limb explosive force against an increased load due to a barbell lifting on athlete's shoulders, starting from a knee angle of 90 degrees. The athlete, with a barbell on his shoulder, starting from an upright position and hands on hips, perform a squat up to a 90 degrees knee angle and maintains this position for 1 second. From this static squat position, performs a vertical jump without make any counter movement downwards to keep out elastic energy contribution. The drop jump test investigates the lower limb reactive force, and it is used to calculate the optimal height of fall that allows performing the best vertical jump. The subject has to fall from a step, height between 20 and 60 centimeters, with extended lower limb, trunk upright and hands on hips. Starting from an upright position with feet at shoulders distance, athlete brings one leg forward and lets himself falling down. After feet contact on the ground simultaneously, he performs a vertical jump. The last one is the stiffness test that has a high importance in the reactive force evaluation. This test uses neuromuscular and muscle tendons bones system reactivity to evaluate the reactive force component of lower limb extensors. The athlete, with hands on hips, an upright standing position and feet at shoulders distance, performs a series of vertical jumps in a fixed time, or a predefined number of consecutive jumps. The first jump may have a counter movement, while the others must be executed with stretched lower limb. In order to accelerate the acquisition and give more attention to the report analysis, I will show you an acquisition only of a counter movement jump, but then we will see all the reports that can be obtained performing all the jumps displayed in the tabs. So, let's start with the CMJ acquisition. We click on New Counter Movement Jump, and another screen is displayed. We select the correct COM port associated previously with the sensor, and we click on this button. Note that for every jump, you have a small paragraph that reminds you how the jump has to be performed. Doing this, we make now the sensor communicating with the computer. Click on the button Enable Video Capture. You can make the software record the video of the trial that you are performing. Now I switched off. Okay, if we press the button Start Online, we can see the raw tracks of accelerometer and gyroscope. To acquire, we have to click on Start Storage, so that the computer starts to record the trial. Once clicked on this, the software firstly waits for a stable phase in which it records offset data. You have to wait in a still position until the bar is completed. Then you can perform your jump. When the trial is finished, it is necessary to click on Stop Storage so that the computer stops to record. By clicking on Save immediately, the previous window is reopened and your report will be displayed. This simple procedure has to be repeated for all the jumps you want to perform. In order to visualize all parameter indexes, I will now load a trial in which the athlete performed all kinds of jumps in the tabs. As you can see, all the tabs are now completed. We can divide jumps into two classes, depending on how many jumps are performed. In particular, counter movement jump, squat jump, counter movement jump with arm, squat jump body weight, and drop jump expect for one single jump, while repeated counter movement jump and stiffness expect for multiple jumps. For the second group, we have, in addition to the current parameter value of each jump, also the average of all jumps performed, the contact time, and the number of jumps performed. So, let's see in detail what the report shows. We have three main regions in this screen. The first region on the middle shows 5 tracks. The first is the global vertical acceleration 1, where you can see the preload phase, here, and the flight phase, here in yellow. The second one is the strength track, which is obtained by multiplying the track above for the subject weight. The third track shows the power profile, and it is calculated from the takeoff to the landing. So you have the first positive area that corresponds to the pushing phase, in which the speed is positive. A negative area, which corresponds to the landing phase, where we have negative speed, and a second positive area, where the subject dampens the fall. There are also speed and displacement tracks. Also, these lattice two are calculated from the takeoff to the landing. Moving the mouse over the track, you can see current values. The second region is that shown on the left. We have 7 bars, each one with its trial result. First of all, we have jump height, expressed in centimeters. This parameter is maybe the most used in jump performance analysis. Subsequently, we have 2 parameters of force, which are related to the takeoff, the first, and to the landing, the second. The unit measure is kilonewton. Then we have the maximum concentric power, which is calculated as the maximum of the product between force and velocity in the concentric phase. This latest is took from the start of the pushing phase to the takeoff. The last 3 parameters are related to speed. The so-called average speed concentric phase is, as told by its name, the average of the speed in the concentric phase, and it is expressed in meters per second. The peak speed is the maximum speed in the concentric phase, while the takeoff speed is the velocity with which the subject starts the flight phase. If I open a multiple jump, such as a stiffness test, you can see that because we have too many jumps, most of the values are not shown. But if you click twice on the bar, you can see all in full screen, and so you have all the values. The third region is on the lowest part of the screen, here. It shows 6 fundamental indexes to evaluate a global performance. In order to visualize them, we have to perform all the jump types written on the formulas. So, for example, for elasticity, we have to perform a counter movement jump and a squat jump. Or, for example, for the coordination, we have to perform a counter movement jump with arm and a counter movement jump. So let's see in detail. The elasticity is descriptive of how much the shortening-stretching cycle influences the jump. In fact, in the squat jump, the preload is left out. So you can see that in the squat jump, we have no preload phase, while in the counter movement jump, we have a preload phase. This parameter must be at about 20%. For example, here we have 17.5%. If it is less of 20%, it means that the subject doesn't correctly use the preload phase. If it is greater, it indicates that the subject doesn't have the capability of express a night performance without preloading. The second parameter is the Bosko Index, which indicates how a subject is influenced by having a load on his shoulders. The jumps that have to be performed for calculating this index are the squat jump and the squat jump with body weight. This latest is a normal squat jump, but with a barbell on subject's shoulders, equal to subject's weight. The coordination index expresses how the arm's use improves jump height. As indicated by its name, is an index of subject coordination capability. Performing a repeated counter-movement jump, it is possible to calculate the endurance, which indicates the ability to sustain a task from the beginning to the end of a trial. So you have the ratio between the first 3 jumps and the last 3 jumps. The task index is calculated in order to view whether the subject performed the test at his maximum faculty. If this index is less than 0.80, the test has to be repeated. The last index shows how work decreases during a repeated counter-movement trial. It is the ratio between the average of all jumps of RHMJ protocol and the single counter-movement jump. So the ratio between this and this. All these indexes have been calculated as illustrated in Bosko's book titled Force Evaluation with Bosko Test. Once finished, you can save or print the report. You can either simply save it on the software, which this button, now it's just save, or it is possible to save raw data as TXT or EMT. EMT is a particular format used by our kinematic software. If you save it in these 2 latest formats, filtered tracks are recorded. If you open the TXT in a second time, the software handles again the trial and the report is shown. TXT files can be imported in Excel. If you do this, you have 6 columns in Excel. The first 3 columns are related to acceleration. So you have the X acceleration, the Y acceleration, and the zeta acceleration. The last 3 are related to the angle velocities. You can then use it for your personal analysis. If you want to print the report, you have to click on the dedicated button here. In this way, you can also save a PDF file if you have a PDF creator installed on your PC. Moreover, it is possible to compare different analyses with this button on the left. Opening trials. It is possible to add an analysis. As you can see, if I open the previous analysis, an histogram for each jump performed is displayed. Now, if I open another analysis, for example the second, histograms associated with jumps performed are added, and the average histogram is updated, and so on. For example, the fifth, okay? You can see that in this we have only the squat jump, so a bar is added to the squat jump. Thank you very much for your kind attention, and I hope to see you in the next sport webinar. Bye.